Hi everyone. Today we're going to continue with our videos on the theory of structural dynamics, and we're going to basically talk about free vibration of multiple degree of freedom systems. After today, you should be able to model any one of the structures that you see in this slide. So even though we're going to look into this little simple house in the middle, the theory that we're going to describe and we're going to discuss applies for any structure that you see in this slide. It could be a bridge, it could be a building with a complex structure, or it could be a high-rise building. So the theory that we're going to discuss applies to every single one of these buildings, but we're going to focus into the little house in the middle. So when we look into this little house, we're going to model it as a 2-degree of freedom system. So what we're going to say is that the dynamic behavior of the house basically is described by the motion of the first floor and the motion of the second floor. And if we know the position of the second floor, if we know the position of the first floor, we are able to calculate stresses, strains, and design our house and our system for any earthquake motion or any vibration motion. So this is the 2D frame we're going to discuss in this series of videos. Now, this derivation is very complex, so it is very difficult to give you the entire thing in just short videos, so I decided to break it down into 4 different videos. So what we're going to do today is probably the most complex video because we are going to present the problem, but we're not going to discuss how to solve it. It's going to feel a bit awkward at the end of the video. You're going to be asking yourselves, what was the point of this video? And then we're going to look into 3 more videos that hopefully everything together will make a lot more sense. So the topic we're going to look today is the dynamic equations of equilibrium in the coupled form. And we're just going to discuss about that. It won't make a lot of sense at the end, but don't worry, watch the other 3 videos and at least things will be a little bit more connected. Now let's look into our idealized system. So it's similar to the one that we saw for the single degree of freedom, but now we're considering 2 masses. Again, even though we're just considering 2 degrees of freedom, this theory applies to every single body, every single system that is vibrating. So as I said in the beginning, any structure will be based on the theory that we're going to describe. For the first mass, we're now going to define a damper between the support and the first mass. Let's call it C1, and then we're going to consider a spring that is, let's call it K1, or the stiffness, let's call it K1, and the stiffness is also between the support and mass 1. Now, the same now applies for mass 2. In between mass 1 and mass 2, there's also a damper, and there's also a stiffness. And this basically describes the damped system in a multiple degree of freedom, okay? Similar to what we did in the first video. We're going to get rid of the damping. Let's just analyze the undamped system. We kind of know what damping does to our structures, what is the things that it affects, but it's just easier for the formulation if we consider the undamped system first. So just imagine it like this: stiffness K1 connecting the support to a mass M1, and then connecting mass M1 and mass M2 another spring with stiffness K2. And again, this is called a 2 degree of freedom system because with these 2 quantities, let's say x1 of t and x2 of t, representing the displacement of mass 1 and the displacement of mass 2, if we know these 2 positions, if we know these 2 displacements, we know everything about our system and we don't have to do any more calculations. Now, the first thing we need to understand is that this house is modeled by this frame. And the first assumption that we're going to do is to say that the mass is basically concentrated at the floor levels. If we consider that mass 1 is basically the mass of the first slab and mass 2 is basically the mass of the ceiling, we're not very far away from reality, and this is a very fair assumption to do. You could say that, what about the weight of people? What about the weight of furniture? That doesn't come close to the mass of the slabs. So we could basically account for these 2 masses, M1 and M2, just by knowing what is the volume of concrete, for example, of these 2 slabs, and multiply by the density of concrete, and that we can get these 2 masses. In terms of stiffness, what is this K1? This K1 is represented by the lateral stiffness of the columns, or in this case the walls, that connect the first mass with the ground, right, with the supports. While the stiffness K2 is represented by the columns or walls that connect the second mass with mass 1. So for any real structure, if we know how to quantify these 2 stiffnesses, we can very simply describe the dynamic system just based on this K1 and K2 and based on M1 and M2. And again, 2 degree of freedom just means that if we know the motion of the first slab and if we know the motion of the second slab, we know all the stresses, all the bending moments in our columns, in the reactions, we can calculate everything we need. So I hope this is clear, and now let's go back and focus into our idealized system. So first consider that we're going to move both masses to the right, and that amount that we're going to move is equal to x. If you look at the springs in this case, the first spring stretched quite a lot, but the second spring didn't, which makes sense because the two masses move the same amount. So just by looking at this this way, we could say that the elastic force of this first spring is only dependent of the motion of mass 1. So no matter what is the position of mass 2, the elongation of this spring does not change, right? So we can say right away that the elastic force acting on mass 1 because of spring 1 has only to do with this variable that we're going to call it x1. So it only has to do with the displacement of mass number 1. And now what about the second spring? For this, let's imagine that the two displacements are different. So let's say that x2 is a little bit bigger than x1. And now we can see that this spring is stretched. And it's stretched the amount x2 minus x1. So we could say that the elastic force in this case, and now it acts in both masses because of equilibrium, it's equal to K2 times the elongation of the spring. And in this case, the elongation is x2 minus x1, is the difference between displacements. Now, just to make sure this equation makes sense, if x2 is larger than x1, this is positive, right? And positive means the spring is in tension. And imagine that this spring is in tension. What is the spring going to do? It's want to try to compress, right? Wants to go back to its original position. So it's going to push mass 1 to the right, and it's going to push mass 2 to the left, and hence the directions of these two vectors. Now imagine that x2 is less than x1. This is negative, and that means the spring will be in compression. The spring is in compression, is going to try to stretch out, and that will push the mass 1 to the left and will push mass 2 to the right, which means these two forces are consistent with the definition of x2 and x1. Now, the next step is to isolate mass 1 and try to establish an equilibrium equation for this mass. If we look at this mass on its own and we use, as usual, the second Newton's law that says the sum of forces has to be equal to ma, we're going to write that minus k1 x1 plus k2 x2 minus x1. So these two forces have to be equal to m1 times acceleration. And then if we take these two forces, send it to the same side, we can rewrite this equation at equal to 0 type of shape. And then the next step is, instead of having a term for k1 and a term for k2, I want to have a term for x1 and a term for x2. So I'm going to expand the brackets here in this stage, and this gives me plus k2x1 and then minus k2x2. And then at this stage, I'm going to factorize x1 in this term here, and this leads me to the first equilibrium equation for mass number 1. That mass number 1 times acceleration, and note here that acceleration is being described as the second derivative of displacement, and now plus a factor that is k1 plus k2 times x1 minus k2 times x2. And again, x1 and x2 are the displacements of the two masses, k1 being the stiffness between the support and the first mass, and k2 being the stiffness between mass 1 and mass 2. Now, if we look at the second mass and try to isolate it, and again we're going to do the same thing, say that the sum of forces equals to ma, and now we only have one force, and that is equal to minus k2 times x2 minus x1, and that has to be equal to m2 times a. Again, we send this to the same side, and then we keep the equal to 0. And again, what we're going to do is to have a term for x1 and a term for x2. And this, again, leads us to the second equilibrium equation for mass 2, that mass 2 times its acceleration minus k2x1 plus k2x2 equals to 0. If we combine the two equations of equilibrium in a system, and we know how to solve it, we could describe the vibration of a multiple degree of freedom. What is interesting to understand at this stage is that these two equations are coupled. And to understand what coupled means in this context, I want you to look into these two terms. This minus k2x2, and in this one, the minus k2x1. And let's imagine that they disappear. If we don't consider these two terms, this first equation just depends on x1. So it's m1 times acceleration plus K1, X2, X1, and does not depend on the motion of the second mass. And if that was the case, we could solve this as a single degree of freedom. We could just say that the natural motion is the square root of K over M, and say that the motion is described by a cosine wave, exactly as we described in the single degree of freedom video. And by the way, the second equation has the same properties. It's an equation that depends only on x2 and has the acceleration and has the displacement. And we could solve it as well as a single degree of freedom. Find the circular natural frequency and find the equation of motion and the cosine wave and amplitude and all those things. Now, we call these equations coupled because these two terms exist, and therefore the motion of the first mass and the motion of the second mass are coupled in the equations. That means we can't solve them. This basically means that the motion of the two masses is interfering with each other, and therefore the calculation is a lot more difficult than it was in a single degree of freedom. And that's a problem, and that's a problem that we're going to try to solve in the next few videos. Now, before I let you go in this video, I want to talk to you about writing equations in matrix form. And matrix form is very, very important in dynamics, even though you might not like it in the beginning. When we consider very complex structures, let's say like the Sydney Opera or the high-rise buildings I showed in the beginning, it's very useful to write our equations in the matrix form. Because it's basically the key to combine the 2 degree of freedom that we're going to study in all these videos and a multiple degree of freedom with 3 degrees of freedom, 10, 1,000, a million degrees of freedom. If we learn how to describe these equations in matrix form, that single equation describes every structure in the world, okay? So it's important that you get used to these definitions. So let's do a little bit of a refresh. And if we have a matrix times a vector, and in this case, matrix is ABCD, and the vector is EF. The way you do this multiplication is you do the first row times this column. So you do AE plus BF, and that's your first term. And if you want to do the second term, you do the second row times this column. So you do CE plus DF. So let's look into these equations of equilibrium, but now written in matrix form that has this look. And let's see if this works. So if we keep this matrix like this, M1, 0, 0, M2, and then this matrix here, K1 plus K2 minus K2 minus K2 and then K2, and these two vectors, this will be a vector of accelerations, and this will be a vector of displacements. Now let's see if with these equations written in matrix form, we can go back to the equations as we described before. So if we look at this first line, we're going to do M1 times X1, acceleration, plus 0x2. So we just get M1 X1. And now plus K1 plus K2 times X1, and this is this term here, minus K2 times X2. And then this equals to 0. So this first line, when multiplied by the vectors, gives you this first equation. Now, the second line, we can test it as well. So we get 0 times X1, that's 0. And then M2 times X2, and that's this term here. And now minus K2 X1 plus K2 X2. And this, again, is what we already described, and that is equal to 0. So there is no necessity to write in matrix form when we talk about the 2 degrees of freedom. And you might think that this is just crazy, that this looks a lot more complicated than this. But this is a lot more powerful because this way to write the equations in the matrix form defines any structure in the world. And it's important that you have this in the back of your mind. Now, to finalize, I want to give a name to these two matrices. This matrix here, M1, 0, 0, M2, we're going to call it the mass matrix. And it always has this shape, M1, 0, 0, M2. And this matrix here, we're going to call it a stiffness matrix. So K1 plus K2, minus K2, minus K2, and K2. So if we just call this mass matrix and we just call this K matrix, we're going to get to this very, very elegant equation. And again, very powerful to understand that mass matrix times a vector of accelerations plus the stiffness matrix times a vector of displacements is equal to 0. And again, this is generalized for any structure, multiple degree of freedom, 100 degrees, 1,000 degrees of freedom, a million, it doesn't matter. This equation defines all of them in a very elegant way. Now, in summary for this video, we learned the dynamic equation of equilibrium in matrix form. We also learned how to define the mass matrix for a 2 degree of freedom system, so M1, 0, 0, M2, and we learned how to define the stiffness matrix K1 plus K2, minus K2, minus K2, and K2. We also discuss the coupled form of dynamic equations of equilibrium, and this part is not important that you memorize. What is important that you have in the back of your mind is that they are coupled, and because they are coupled, we don't know how to solve. And we're going to use the next 3 videos to explore different solutions and explore different ways to solve this system. Thank you for watching and have a good day.